Good morning. So, my name is Manoj and my team number name is Sudarshan Vijay. So, our title is Predicting Video Game Sales with BART. So, for the introduction, in this research, we explore how a modern Bayesian technique called Bayesian Additive Regression Tree or BART can help predict sales performance in the competitive and fast changing video games industry. So, our aim is to not just predict how much a game will sell, but to do with the measure of confidence, which helps in planning and decision making. So, our more next one is a motivation and problem statement. So, forecasting video games is a challenging task. Unlike many consumer products, video game sales are heavily influenced by trends, player performance, and console popularity, and even release timing also. So, a single influencer review or a viral moment can make or break title performance. So, traditional models like linear regression assume a straight line relationship between variables which does not match the real world behavior of game sales. So this model are not good at handling non-linear patterns or interactions between variables. That is why we use BART, which captures the complex relationships automatically and provides a full distribution of predictions instead of single value. This is particularly helps when companies want to understand the risk involved in over or under estimating future demands and the data set and the forecasting task. We use the data set from Kaggle titled Video Games Sale with Rating. It includes about 16,000 games titled released between 1980 and 2017. And these games spans across major platforms like PlayStation, Xbox, and PC, etc. So the data set includes features such as game in the game platform it will be having PS4, Xbox and PC everything, and in Jan we can see action sports, shooting or everything exactly. And we will be seeing publisher and year of release and regional sales like North America or Europe, China, Japan, etc. And the target variable is global sales in millions of copies. Since the sales values are skewed, with many games selling very few copies, a few selling tens of millions, we applied a large transformation to normalize the target and stabilize the variance. And this is the data. And first, rational for choosing BRAT means why did we choose the BRAT? So BART stands for Bayesian Additive Regression Tree. It works by combining the output of many small regression trees. Each tree contributes a little bit to the final prediction. Because the trees are small and weak individually, the model avoids overfitting. The what makes a bird different is its a Bayesian nature. Like it adds priors to the control overfitting, and it does not just give a single prediction but a full probability distribution. It allows us to calculate credible intervals, which gives us a range in which future sales are likely to be fall. So compared to other models like XGBoost, BERT requires less tuning and provide more interpretability uncertainty, make it a great choice for business forecasting. So this is how bot learns. Like first, it starts with a set of shallow trees that together approximate the average sales. Then it uses MCMC Marco chain Monte Carlo to intermittently replace refine each tree by fitting the residuals left by other trees. And each iteration applies tree operation like growing new branches, pruning them, and swapping splits or changing split rules. And after enough iterations, like it's called burn-in, it gathers sample from posterior distribution. So this process allows bird to learn from patterns without making strong assumptions about the data structure. So optimizing running time. So initially our Python implementation took about 18 minutes for 200 reads and 400 sweeps. So to make it more efficient, we vectorized our code using NumPy, which reduced the operations, and we use Numba, a just-in-time compiler to speed up the loops. And this optimization allows us to experiment and iterate quickly while maintaining the model integrity. So model evaluation metrics. We used around 80 to 20 split train and test our model. We also created unique features like platform gen combination and used install base size as proxy for market size. And our custom BART model achieved uh, R square is 0.872 and MAE 0.042, and as we can say RMSE is 0.537. So this indicates a strong fit to the test data, suggesting BART was able to capture the underlying complexity of sales behavior effectively. So next, we'll be comparing with other models. Like we use so many models. So in that, we compared with the random forest, XGBoost, and linear regression. So random forest good performance with R square is 0.2, but no uncertainty estimated. In XGBoost, we can see fast and scalable, but had lower R square around 0.79. Linear regression very high on log transform data, but performed poorly on Rascal due to oversimplified assumptions. So only BART gave us both good performance and credible intervals, making it most business-ready model among the ones we tested. And this is the graph which we can see. And the key insight for the stakeholders, like business insights. So the size of the console user base is a major sales driven. Low certain journal platform combinations consistently perform better. So, for example, action games on PlayStation like that, and even minimal domain knowledge when encoded as features can significantly boost model accuracy. So, with a BOT interval predictions, business teams can better play for uncertainties like stock shortages or overproductions, etc. So this is the limitations and the future direction. So the dataset lack factors like marketing budget, user reviews, and seasonal discounts, etc. like that, which impacts the sales. And but slows down it with very large dataset unless GPUs are used, and the sales for Indian games often include many zeros, needing more flexible likelihood models. For future work, we plan to incorporate social sentiment and pricing history and try GPU based version like Boson brought like that, and building an interactive dashboard for real time forecasting of upcoming titles. So these are the references we have which we have took from like Kaggle video games sales with rating primary data source, and tools we use is NumPy and Numba, etc. And but and that's it. Thank you. And my friend will be saying the code.
Good morning. This is Sudarshan Vijay. So I will be explaining the codes for today. So at first, project title is predicting video game sales with Bayesian additive regressive tree BART. So at first, we need to select the data set. The chosen data set for this project is the video game sales data set, which includes detailed information on various video games released across platform. The data set provides key features such as genre, platform, publisher, release year, regional sales figure. So the dataset sources from we took it from Kaggle, and the problem type is regression, which is like predicting the global sales in millions of copies. The primary model implemented is Bayesian additive regression tree, a non-parametric Bayesian regression model for benchmarking and performance comparison. The project also includes random forest, XG, boost regressor, linear regressor as a baseline. Reason for choosing BART are particularly suited for complex and non-linear dataset such as video game sales data. So BART also offers the flexible modeling of interactions and non-linearity without explicit feature engineering. Bayesian uncertainties estimates providing prediction intervals instead of just point estimates. Interpretability as it combines prediction from many small trees with posterior reasoning. So at first, we'll be importing the essential libraries for data handling and visualization such as Pandas, NumPy, Matplotlib, Seaborn. And we are also importing modules for data pre-processing and model evaluation such as train and test split, one hot encoder, column transformer pipeline, simple imputers. Then we are also importing machine learning models such as linear regression model, random forest model, XGBoost, and decision tree model used in custom bot implementation. At last, we will be also evaluating the matrices with the mean squared error, mean absolute error, and R square square. Then at first we'll be loading the data, which is loading our data set. After that, we'll be selecting the relevant columns and defining features and target objectives. This step focuses on selecting the most relevant columns for the from the data set that will be used for model training and separating the features from the target variables. So at first we'll be selecting the relevant columns. So we are choosing columns that are meaningful for predicting global video game sales. We include columns related to platform, genre, publisher, and regional sales, as they are the factors that can influence the overall sales of the video game. Since the target variable global sales is essential for supervised learning, any rows with missing target values are dropped. This ensures that the dataset used for training has valid target values. So here the X is the feature set. We drop the global sales column to create X, which contains all the independent variables. And Y is the target variable. It's just the global sales column, which we will try to predict based on features in X. So the outcome will be the data contains only the relevant columns. Rows with missing global sales values are removed. The feature set and the target variables are separated and ready for pre-processing and training. Here we can see the first 5 columns of a data set. After it, we are like trying to visualize the distribution of the global sales features in the dataset to understand its spread, detect skewness, and observe any potential outliners. This helps to get an initial sense of data before training and any machine learning models. So the output will be a histogram showing the frequency distribution of global sales across 50 bins. The kernel density estimate curve overlaid on the histogram offering a smooth estimate of the data distribution. The plot will display the global sales in millions on the x-axis and the count of record in each bin on the y-axis. From this plot, you can access whether the global sales are eventually distributed skewed toward a lower or higher level if there are any noticeable outliners. So the another so next we are visualizing the how global sales vary across different game genres. A box plot is used to show distributed of global sales for each genre, highlighting the median, interquartile range, and potential outliners in the data. So the expected output is the box plot where the x-axis represents the genre of the game and the y-axis shows the global sales in million. The plot will also display the median global sales, interquartile range, and outliners will be displayed as the individual point beyond the whiskers of the box. The plot will reveal which genre have higher and lower global sales, providing the insight into the spread and consistency of the sales across the different genre. So the next we are visualizing the top 10 platforms that contributed the most of the global video sales. The bar plot is used to show the total global sales for each platform, allowing comparison of the platform performance in terms of sales. So the bar plot where the x-axis represents the top 10 platform values and y-axis shows the total global sales for each platform in million. Each bar will represent a platform with its heights corresponding to the total global sales. The plot will display the platforms in descending order of the total global sales. The rotation of x-axis labels ensure the readability of the platform names. This plot will provide insight into which platform dominates the global sales in the video game industry. So here we can see that the PS2 is the highest selling global sales here. So the next step is the pre-processing. The objective of this code is to set up a pre-processing pipeline for both categorical and numerical features in the dataset. Pre-processing ensures that the data is clean, formatted, read for machine learning models. So here we are doing the categorical features. The list categorical features contains the name of categorical columns such as platform, genre, publishers, and the data set. In this, there are like two main steps. Imputers. Simple imputers is used to fill in any missing values in categorical features with the most frequent value in that column. And the encoders, one hot encoder converts the categorical variables into a one hot encoded format, meaning each category will have its own binary column. So the next one is the numerical features. The list numerical features contains the name of the numerical column such as the years, the sales, like the country sales reports such as the North America, Europe, Japan, etc. So here we also have the imputers and scalars. The simple imputers replace the missing values in numerical features with the mean of respective columns. This ensures that the missing data does not negatively impact the model. The standard scalar standardizes the numerical features by scaling them to have a mean of 0 and a standard deviation of 1. This is helpful for many machine learning algorithms, especially those sensitive to feature scaling. So the expected output, the pre-processed process pipeline is now ready to be used with the machine learning. And when fitted on the data set, it will fill the missing values in categorical columns with most frequent categories, convert categorical features into one hot encoded format, and fill missing values in numerical columns with the mean of a respective column. And then at last, we'll standardize the numerical features for the model training. And our next code objective is to split the dataset into training and testing subset. This allows the model to be trained on one portion of the data and evaluated on another unseen portion to to assess its performance. So first we'll be seeing the train test function, which splits the features and target into training and testing data set. So the parameters used are the X, which is a feature matrix containing all the input variable, and Y, which is a target variable, which is in this case is a global sales. Here our test size is specifies that the 20% of the data will be reserved for testing and the remaining 80% will be used for training the model. Random state 42, this ensures that the split is reproducible. Setting a random state ensures that the data split remains the same each time the code is run. So the expected output will be the training set is 80% of the data. We will be using it, the testing for the 20% of it. Then we will be using the target values for training set 80% of the data, then target values of testing set for 20% of the data. Our next code shows the evaluation matrix is to define an evaluation function that calculate the display the performance of a regression model on test data. This function helps assess the accuracy and predictivity power of the model by computing common evaluation matrices such as RMSE, MAE, or R square score. So root mean square error measures the average magnitude of errors in prediction, giving more weight to larger error. And then the mean square error computes the mean square error. Then we take the square root to get the root mean square errors. So, and the next matrix is the mean absolute error, measures the average absolute difference between the predictor and actual values. It is less sensitive to large errors compared to root mean square errors. And the last one is the square, which is a coefficient of determination, represents the portion of variance in the target variable that is predictable from the features. A higher R square value indicates a better performance. So at first we'll be seeing about the linear regression model. To train and evaluate a linear regression model for predicting global video game sales using a pipeline that includes pre-processing steps, data encoding, categorical features, and scaling numerical features. Pipeline is created that first process the features using the pre-processor, then applies linear regression model for regression task. The model is trained on the training data set, X-train, Y-train, and the performance evaluated using the evaluate function. Evaluate function calculates the performance metrics such as the root mean square, mean area, and R square for a linear regression model. So here our output is for RMSE, which is a 2.84, and for MA, which is 0.00 million sales, and for R square, it is 99. So next model is the random forest model. To train and evaluate a random forest model for predicting global video game sales using a pipeline that handles the pre-processing and model fitting. Pipeline is created, integrates the pre-process steps such as the missing data handling, encoding the categorical features, scaling the numerical features with the random forest regressor. The model is trained on the training dataset using 100 decision trees and a random state of 42 to ensure the reproducibility. The evaluate function computes the evaluation matrices. So here the RMSE for random forest is 0.75 million sales. The MAE is 0.041 million sales, and R square is 0.82, which is 80% of the variance in the data. So our next model is XG Boost. The model is trained on the training dataset using the 100 estimators and a learning rate of zero point 0.1. The evaluate function computes the evaluation matrices. For XG Boost model, we are having a RMSE of 0.85 million sales, MAE of 0.05 million sales, and R square is 79% of variance in the data. So next we'll be using a custom BART like model using in decision tree with residual fitting and shrinkage. To implement a custom BART model using a series of decision tree that iteratively fit the residual of previous prediction, applying shrinkage to reduce overfitting. This model aims to predict the global video game sales and provide uncertainties interval around the predictions. The custom BART class is initialized with key hyperparameters, number of estimators, maximum depth of decision tree, which is a max depth, and learning rate. The fit method trains the model using a residual fitting approach. First, we'll be initializing the prediction as zeros. For each iteration, fit a decision tree on residual. After that, we'll be updating a prediction by adding the tree prediction. The prediction method generates the prediction for new data by summing the outputs of all decision trees scaled by the learning rate. Prediction interval method estimates a confidence interval by calculating the lower and upper percentiles of predictions from all decision tree. So the custom bar training and evaluation. So here we will be first transform the training and test features using the preprocessor pipeline. Scale the target variables by using standard scalars to normalize the values for better model fitting. And we'll doing the model training. Initialize the custom bot model with 300 estimators and the t depth of 2 and a learning rate of 0.05. Then we will be fitting the model on a transform training data and scale target. Then we'll be generate a prediction on transform test data, inverse transform the predicted values back to the original scale using the Y scalar. Then we are doing the evaluation metrics for BART. So here we are getting the RMSE as the 0.51 million sales, MAE as the 0.041 million sales, R square as the 87 percentage, which gives us the better accuracy than any other model right now. So the feature performance to visualize the top 15 most important features used by random forest model for predicting global sales. The feature importance value indicates how much each features contribute to the model decision tree making. So here we'll be extracting the models and features name. Like access the trained random forest retrieval model for pipeline. Retrieve the features name after pre-processing using the pre-processing dot get features name out. Then we'll be doing the feature importance calculation. Then we are also doing the sorting and selection plotting. So the expected output will be the plot will display the top 15 features contributing the most of the random forest model predictor, allowing for visual understanding of which factors, example, platform, genre, publisher, etc., have the greatest impact on the global sales prediction. So next we are visualizing the prediction intervals generated by the custom bot model, showing the range within which true global sales values are expected to lie. So here we are doing the prediction interval calculation. BART model dot predict interval calculates the lower and upper bound of the prediction interval. These intervals reflect the uncertainties, and here we'll be plotting. Use the matplotlib to create a plot with three main components: prediction interval, actual values, predicted values, and we are doing the customization. And the expected output will be this paragraph, this bar graph. Then we are also doing comparing the actual and predicted random forest, and this is the scatter plot for it. Then we'll be showing the linear regression prediction scatter plot, then xg boost prediction scatter plot, then our custom bot prediction scatter plot. So in conclusion, this project successfully demonstrates how advanced machine learning models, including ensemble methods like random forest, XGBoost, and a custom bot implementation, can be used to accurately predict video game global sales. The BART-like model added the benefits of predicting intervals, making the model not just accurate but also interpretable. Overall, the structured pipeline from pre-processing to evaluation ensured a robust model performance, meaningful insights, providing the values of combining data science with interpretable for sales forecasting task. Thank you.